So if you made it here, you likely had an easy time with the previous lesson, with the exception of maybe the multiple choice matching. Maybe it was a little bit trickier. But you may be thinking like, Mr. Wright, I thought this was about integrals. This unit was about integrals, and we were just studying slope, and that's derivatives, right? So what do these differential equations have to do with integrals? How is this an application of an integral, right? And that's a smart question to ask. I want to start to answer this question by posing a very simple differential equation. So my differential equation is going to be dy dx equals, let's say it's equal to 3x squared. Okay. Now, what we're doing in this lesson is we're solving differential equations, and solving means to find a function. Solving means to find a function whose derivative is represented by the differential equation. So in other words, the solution to this equation is the function we would have started with. Okay, well, that is just an integral. So the solution to this particular differential equation is just the integral of 3x squared with respect to x. There's no y in this equation, so this is a very easy one. And then we will say this is x to the third, and we're going to double check that this is the correct integral by taking the derivative, and the derivative of x to the third is 3x squared. You know how to do that at this point in your math career. We'll say plus c, because there's actually many solutions to this particular integral. Okay, so this solution to this integral is also the solution to this differential equation. And if you're like, well, that was basically just an integral, you're right. So solving differential equations in their most basic form is just integrating. Now, this is called a general solution of my differential equation. It's general because we don't know what this constant is. Because remember, this could be, and I'll show you what the graphs look like. This could be any number of functions like cubic x to the third functions, depending on what the value of that c is. So in this case, that c shifts it up and down, right? My particular solution would be any one of these graphs. Okay, so we've done this before. What we would need to find that is an initial condition. So let's say we also know that f of 0 equals 1 is my initial condition. So then I would plug in 1 to the third, 0 plus c. 1 plus c equals 0, c equals -1. And then my particular solution, this is called, would be this. So this would be my particular solution to this differential equation. Okay, so that's the connection to integration. And if you're like, that seems really easy, why do we need a whole lesson on this? You're right, it gets more complicated than this. So let's look at a more complicated example. So we've been solving differential equations since we started integration, but this is what's new. So notice, like, and this was true in the previous lesson too, our differential equation is now a function of x and y instead of just x. So here's how we're making this harder. This, by the way, is called a separable differential equation. And when you get to college after another semester or two of calculus, you can take a whole class on different types of differential equations. This is the easiest flavor, but they get pretty challenging because of the complicated relationship between integrals and derivatives. Differential equations is also the only math class I've ever had to retake in my life. So if you're curious about how that worked, you're welcome to ask me at some point in class. So this is a separable differential equation, and that name, I give it to you because it's useful to know. Separable means we're going to separate the variables and the derivatives operators. So I'm just going to rewrite it to start. And this is going to be cool how this works out. It's super logical and elegant. So what I want to do is I want to get all my y's and dy's on one side and all my x's and dx's on the other side. So the first thing I'm going to do is I'm going to multiply by dx on both sides. For kind of obvious reasons, it gets rid of the dx on the bottom and gets it over here by the x squared, which is what I want. And now I have just dy, and I have a y on the bottom, so I'm going to multiply by y on both sides. So I have y dy equals negative 2x squared dx. Okay? So I'm treating that derivative as like sort of the separable two different pieces. So there's the rate of change of y and the rate of change of x. Now, here is where the cool sort of elegance of this comes in. I'm going to integrate both sides. And notice now I have an integral of y with respect to y and an integral of x with respect to x. They're totally separate. So I just integrate using the same integrals, sort of integral skills that you already have. So on the left, I'm going to get y equals, or sorry, y to the, what am I trying to say, y squared over 2, right? Because the derivative of that is just plain old y. And then here I get x to the third, and then my coefficient is negative 2/3. It's just a power rule integral. And then I'll just do 1 plus c. So technically I should do 2, right? Because I took an indefinite integral on both sides. Here, I'll show you real quick why I can just do 1. So let's say I did do, I'm not going to use c because they might not be the same number, right? But let's say I did plus a to represent that one constant, plus b to represent that second constant. What I would likely do at some point is I would do, I don't know, minus a on both sides to combine them, right? And then I'd get like b minus a on the right hand side. That's just another constant, right? So like there's never a situation where I couldn't combine them. So instead of making 2 on both sides, I just kind of do that step automatically and just give one side, doesn't matter left or right, a plus c. So that's the only time you're going to take an indefinite integral and not write a plus c ever in your calculus career is when you have them on both sides. Okay, now we want to solve for that c. So we have this equation. We were given the point f of negative 3 equals 4. So negative 3, 4. So we'll just plug that in. So we'll get 4 squared over 2 equals negative 3 it was, right? Over 3 to the third plus c. And then I'm gonna do that math here. So I get 16 over 2 is 8. And then what do I get here? Negative 27 over 3 is negative 9. And then negative 2 times negative 9 is 18 plus c. And you can do those steps in your calculator if you can't do them in your head. So this obviously gives me c equals negative 10. Okay? So remember, my solution here is going to be an equation. So I'm going to go back up here to the results I got from integrating. And I'm going to have y squared over 2 equals negative 2x to the third over 3. And then I'm going to plug in my c. So I'm going to say minus 10. And this is the solution for my differential equation. On the AP exam, it's fine to leave it like this. And this like looks kind of ugly because it's not solved for y. They will sometimes tell you to isolate y, in which case you should, and you're going to practice that on this Delta Math lesson as well. So I'm going to do times 2 on both sides. That gets me y squared equals negative 4/3 x to the third minus 20. And then I'm going to square root both sides. So that gives me y equals the square root of that whole mess. X to the third, there we go, minus 20. Now, at some point in your math career, you guys learn that when you take the square root of x, let's say I had, I don't know, x squared equals 9, and I took the square root of both sides. You would say x equals plus or minus 3, because either of those make the original equation true, right? Negative 3 squared is also a positive 9. We're going to do the same thing here. We're going to say plus or minus my square root, and then I'm going to check my initial condition. So my initial condition had a positive result, right? So that means I don't want the minus, I just want the plus. Okay, but you have to check that. So I'm going to say, as my final answer, y equals the positive square root of all of that. But if my initial condition had been negative, so let's say that it was f of negative 3 equals negative 4, I would have kept the negative result instead, because otherwise there would be no way to get that negative number. Okay, so this is the solution to my differential equation, and I think the hardest part is actually solving for y, which you rarely have to do on the AP exam.